Alrighty. So I'm going to pass the exams back to you. There are no marks whatsoever, just like with the first exam, because I scanned everything and I used the scanned version for grading purposes, which turns out to be great for me because I can, log into Google Drive, from anywhere on any computer and actually resume the grading part of my activity. There's no need for me to carry all this stuff around. So I'll just separate it into two piles and start one pile from one end and the other pile from the other end. So if you cannot find yours in one of the piles, just wait for the other pile to get to you, and it should be in one of the two piles. I also fixed my scanner, so instead of only scanning like 10 pages at a time, which is kind of painful, I can now scan like about 40 pages at a time, so that's a lot faster. It's a double-sided, duplex, scanner, so it just goes like like that. The most painful part is to use this thingy to destaple your exam, and then have to restaple it, obviously. Yep.
Did you grading use it yet?
No, not yet, but I have all the solutions, so that's what we'll talk about today, is to talk about the solution first. Okay, so we'll start with number one, question number one. I had 3 midterms last week, including cisp 360, 310, and 440. The first question of the second exam of cisp 360, I had to restart like 6 times because every time I think I got the grading rubric done, I would come across an answer that is unaccounted for, and yet it is not completely wrong. So I have to go change the rubric and then start all over again. So hopefully for this class, I'm going to scan through all the answers first before I determine the rubric. Yep, go ahead. Are you recording? I should be recording because I set up a timer to have it start automatically. So here, yep, it is recording. All right. So this is the first question. When you check your grade, even though there's no grade available because I haven't graded all the questions yet, what you want to do is to go check your quote-unquote grade. I think the rubric will still be disclosed even though I have not selected anything. Is that correct? I mean, has anyone checked? Okay. So that is the important part because at least you will be able to read the actual answer. Okay, so this is the answer of exam 2, question number 1. It's broken up into 3 different parts. And the idea is if I break it up into different parts, you can at least get partial credit. If you get one of the parts right, you get the partial credit for that particular part, or step in this case. So step 1, since some of you have your exam back already, if not, you can kind of remember what the question was. Step 1 was, if I give you a class of only 2 students, I want to know the chances of having both students having exactly the same birthday. And I'm assuming that each year only has 365 days, so I'm not taking into consideration leap days, leap years, and so on and so forth. So what are the chances that 2 students in a class of exactly 2 students having exactly the same birthday? Well, how many choices do we have for the first student? 365 out of 365 days. And once the first student has disclosed, okay, my birthday is blah, 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 what about the second student? The second student only has how many choices out of 365? 1 out of 365. So you have 365 over 365 times 1 over 365, and that will give you the chances of having 2 students having exactly the same birthday. So the answer is just 1 over 365 because the first number simplifies to 1. Yep.
So what about the way that you did it on the practice exam? The way you did it, you said if they don't share it, find that probably.
It will work for step 1. For step 1, it will work because when you only have 2 students, they are complementary. In other words, the chances of 2 students having the same birthday is exactly the complement of the 2 students not having the same birthday. So you can take a 1 minus and then 365 over 365 times 364 over 365. They will come up to exactly the same number. So if you use that approach for step one, it will still be okay. But that's a special case because it's a special case because only when you have two students that it becomes a complementary type of thing. When you have three students, it is not complementary anymore. Because there's a very slight chance that all three students have exactly the same birthday, so it's not a complementary of each other. Okay. So are there any questions about step one, where the class size is only 2, and we are just trying to calculate the chances of both students in that class having exactly the same birthday? If there are no questions, we'll move on to step 2. Step 2 basically says, now we have a class of 3 students, and I only want to know what are the chances of having 2 students, exactly 2 students, having exactly the same birthday. In other words, I do not want to count the chances of having 3 students having the same birthday, just exactly 2. That is the question. Okay? So if we order the students, okay, so we'll just name the students A, B, and C, okay? So there are 3 exact students. We have A, B, and C. And we'll only consider one case at a time, okay? So if I just walk into the classroom and I ask, okay, student A, what is your birthday? Does student A, since he or she is the first one that I asked, does that student have any constraints? No constraints. So that means student A can choose any day out of 365. Is that making any sense? Okay. Now for student B, I want student B to be different from student A, have a different birthday. So student B now has a constraint of, well, one fewer day, because one day is already picked by student A. So student B has 364 out of 365 days to choose from. Is that part okay so far? What about student C? Student C has to share a birthday with either A or B. What are the chances? It's not 1 over, it's 2 over. Because in this case, student C can share a birthday with either student A or student B. But that's only one way to arrange it, okay? In this particular configuration, A and B are different, but C can be the same as either A or B. So how many ways can we arrange it to have exactly 2 students in a class of 3 to share the same birthday? Okay, well, let's take a look at A, B, C, okay? So this time I have C either being the same as A or being the same as B. What are the other configurations? There's one more configuration. So we can have A, B, C, and this time we have this is actually accounting for 2 cases already. So what other cases do we have to consider? Okay, A and B can share the same birthday, and that's it. That's the only one that we have not accounted for. Okay. So now the question is, how do we add this one to what we have on the board? That makes it 3. Because this one accounts for 2, and then this is just adding 1. I'm gonna have to work out the math a little bit more, but I'm going to make this more clear. There's another way to look at this too, but I'll talk about it later. Okay, now we generalize to 30 students. Okay, when you have 30 students, the first one that I need to think about is, what if I want the first 28 students to have different birthdays? That's an easy one, right? Yep, go ahead.
Is that your final answer?
No, I have not. That's not. It's not consistent with the notes yet, so I have to update the notes. I have to think about it a little bit, just a little bit more, because I kind of miscalculated in my notes, because I thought there are more ways to arrange the equal birthdays, but there are actually not. Basically, it is this number times this 3 comes from the number of ways that you can choose 2 out of 3 students. That's basically what it is. Right? Okay. Moving on to the step 3, which is the general case. So this one is not finalized yet because this number should be out. I should just keep this 3 here. And 3 over 365. In step 3, we are looking at a class of 30 students. So with a class of 30 students, I want the first 29 students to have different birthdays to set up, the background. How many ways can I arrange that? Well, the first student has 365 over 365 days to consider. The second student, 364 out of 365. The third student, 363 out of 365. And then the 29th student has 365 minus 28 divided by 365 days to choose from. Are we still doing okay so far? Okay, so this will account for the first 29 students. Okay, they will all have different birthdays. So now we need to account for the last person, who is going to share a birthday with one of the 29 students. Okay, so that seems to be just 29 over 365. But that really is not the case because there are more ways to choose, how to pair up the students. So the total number of ways to choose to pair up the students is actually C32, which is out of 30 students, you choose 2 to pair up. So this is the actual answer. The way I did it here is also incorrect. Actually, that might be 30 times 29. That's a permutation. So this one is incorrect. It is. This would be the right answer. Are we still doing okay so far with this particular question?
So the first portion, permutation of 365, 29 out of 365.
Right. So this portion is P 365 29 over 365 to the power of 29. That's the first portion. The second portion is the number of combinations of choosing 2 students out of 30 divided by 365. Because this determines how many ways you can pair up students. Yep. Mm-hmm. Oh, okay.
Oh, that one didn't go around all the way.
Oh, okay.
I don't know about this one.
We need a better way to route it.
Yeah.
Okay. Has anyone all seen this pile, or okay? So I'm going to change the key also, because when I worked on the key, I was using a wrong assumption. This is the correct assumption. Are there any other questions? Yep.
For the last part, why you pick 2 out of 30 again? Where's the 2 come from?
Why is 2 out of 30? Because 2 out of 30 students need to have the same birthday.
But basically, the first one, so you pick 29 students that have different birthday. After that, you pick 1 student.
You pick one to be the same as the other one. But how many ways can you arrange it? That's the question. You don't want to double count it either, because okay, so in this case, when I count student C to be the same as student A, okay, how should I put it? Yep. Oh. Okay, he needs to. Okay, so apparently that is not a good way to route exams. Okay, so if I put a 2 here, okay, that means C can match up with B. C can also match up with A. That's why we have a 2 here. but it's not accounting for every single possible ways to pair up the students. Because out of 3 students, how many pairs can I make out of it where the order is not important? We only got, we have two ways to order pairs of students, right? So we have pairs like AB, AC, and BC. These are the 3 possible pairs. BA is not considered a unique pair because it is still the same as AB. Order is not important. So this 2 is not the whole story. It needs to be a 3 here. And that 3 comes from the number of ways to choose 2 out of 3 items. Is that okay?
Okay.
So it's the same argument here where we have to consider, how many ways can we pair up students out of 30? Out of 30 students, we just need to come up with a single pair. So now we have, A, B, AC, AD, AE, and so on. So all of those ways are different ways to generate a pattern where we have 29 students having different birthdays, and 2 of them, the remaining one is the same as one of the other students. Is that okay? All right. Yep.
For the practice exam, did we come up with a different number?
The practice exam is a little bit different, but that's a key difference. In the practice exam, I was asking, what are the chances that someone, at least 2 students share the same birthday?
Right.
Which is not the same as asking exactly 2 students sharing the same birthday. So in the practice exam, it will also include the chances of what about 3 students sharing the same birthday? Any 3. Any 4 students sharing the same birthday? Any 5 students sharing the same birthday? So that's why the numbers work out to be different. But in this case, I was asking for the exactly 2 students, and that's kind of threw a wrench into what we did with the practice exam. But it's still related because the first 29 students still have all different birthdays. It's just how do you treat the last student who has to share a birthday with one of the 29 students that have different birthdays. Okay, so that's question number 1. Are there other questions about this one? And I have to, as I said, I have to update the key so that it is correct. Question number 2. Okay, so for question number 2, the answer or the key is also in your homework assignment. So even though it has no score, you can still see the key. This one I really kind of like. Okay, it kind of works out to be, I would say, the right level of difficulty. It's not too bad. It's not too easy. It's just about right. Okay. So we start off with 3 given facts. So what I'll do is I'm just going to work on this by hand. Or do you guys just want me to read it out of the whiteboard? I mean, that's kind of boring. Doesn't matter, one way or another. Okay, so when you look at your exam with question number 2, and by the way, can anyone guess where this comes from? There's a particular reason why I picked this, C is the same as X and Y. Okay, I'll just go ahead and highlight this. Especially for those of you who took CISP 310 in the spring semester. Well, in the fall semester, excuse me. What is C? Okay, think about a half adder in CISP 310 in computer architecture. C is the carry flag. Okay, so I was basically just using that as an example for this particular question. But you don't have to know that, okay? There's no need to know that ahead of time, and knowing it is not going to help either, okay? Because I'm not asking what is a half adder or what a half adder does. I'm asking you to prove a theorem. So when you look at the 3 things that are given to you as facts, okay, the second and the third ones are easy. In other words, when you look at not C all by itself, it is already in CNF. It's already in conjunctive normal form because it is a single item. Any single item or the negation of any single item is already in CNF. So in this case, that's already in CNF. X is even easier. If there's no negation in this case, it's just a variable, so it is also in CNF. The only one that is not in CNF is this guy here, and it cannot be in CNF because it's using operators other than conjunction and disjunction. Okay, the equivalent to the double-sided arrow is an operator that you cannot use in CNF. Okay, so the first thing we have to do is to convert this into CNF so that it is in CNF. And this particular rule, which rule did I use to turn it into this form? I'm turning A is equivalent to B, to A implies B, and B implies A. Is that okay so far? Okay. So I break it up into two parts. And in each part, now because of this conjunction here, what I need to do is to look at each part, turn that into CNF, turn that into CNF, and then the whole thing is going to be a CNF. So that's kind of neat because there's not much interaction between the two parts. Or I should say there's exactly no interaction between the two parts. Okay, the next step is kind of mixed here because I was doing two steps at the same time. So first one is I take this one here, which is C implies X and Y, and turn it into not C or X and Y. That comes from A implies B is the same thing as not A or B. Okay, are we still doing okay so far with all this stuff? Okay. And I do exactly the same thing to the other side as well. So on this side, we have X and Y as one whole thing, implies C. So what I do is I invert or negate the first one, and then turn the operator to an OR, and then the second one is preserved. Are there any questions about how I went from the first row, which is this particular formula, to the second row, which is the other formula over here? Are there any questions about this step? No questions? Okay. But once we get here, the right-hand side and the left-hand side are treated differently, because what I did with the left-hand side, which is this one here, is to apply, okay, which rule did I apply to get to the next line? Distributive law, okay? I used the distributive law on Boolean algebra in order to come up with the next row. So not C or, and then the conjunction of X and Y is basically not C or X and not C or Y. Okay, next question. Is this, just as a component, is it already in CNF? Yep, it is already in CNF, so I got one part done already. So now I look at the other side. The other side has a negation on the outside, a conjunction on the inside. And I know that this is not going to work, it's not in CNF. What can I do about this? It's not a distributive law in this case, because the negation is on the outside, not in the inside. The only thing I can do about this is De Morgan's law. So De Morgan's law allows you to distribute the negation to the items in the inside, but you have to change a conjunction into a disjunction, or vice versa if you start off with a disjunction. So that's why I end up with the negation of X, the negation of Y, but the operator, the original operator of a conjunction now becomes a disjunction. Okay? But once again, if you look at the entire right-hand side, is that already in CNF?
Yes.
It is already in CNF. Okay? It is one subterm of a CNF, or a formula that is already in CNF. So at this point, I have the whole thing done already. Well, as far as this little expression, turning it into a CNF, this is already a component of a CNF, and this is already a component of a CNF, and here's a conjunction. Okay, so that's good. And on the other side, we have this entire thing as a component of a CNF, so I can just use the entire thing over here. I just took out the inner parentheses because it is associative, and we don't have to specify the order of the ordering of the parentheses. So that's why I can turn this into a formula that is in CNF like the following. Are there any questions about this step? So there's partial credit for this one too. If you get this part right, or at least go through a few steps that are in the right direction, there'll be some partial credit. Once we have all the components in CNF, the conjunction of all of these components would also be in CNF. In other words, I take all of these things and we combine them together, and I'm just trying to find the scroll bar so I can scroll it to the other side. Apparently, I cannot do it. Okay, so that's fine. So I take the first one, I take not C as a component, I take X as a component. But I also have to add one more thing to do a proof by contradiction. I have to negate the theorem that I want to prove. The theorem that I want to prove is the negation of y, but I cannot put the negation of y into the whole system. I have to put the negation of the negation of y. Double negation is canceling each other, so I basically put y all by itself into the equation. So that's why we have one term here. So what I need to do now is to look at this entire thing, okay, this entire formula in CNF, and then apply resolution by refutation. Resolution by refutation basically asks you to identify components. One has the non-negative version of a variable, the other one has to have the negative version of a variable. You will combine those two components, get rid of the variable where it is negated on one side and not negated on the other side, and combine the remaining parts together. So this is what we need to do at this point. If I zoom out enough, no, that won't work either. I actually wrote down here, 3 and something, which is actually indicating which one it is combining with. So what I'm doing here is I'm combining this with y here. So by combining this term, which has a negation of y, with this term here, which is just y all by itself, I cancel out this term here, and I have what is remaining is just not x or c. Can I answer your question?
I did the CNF to the second step, but when I started this, I distributed everything inside of it.
Okay, so you're talking about the previous one? Are you talking about?
Yeah, when I did the CNF, I did the second step, but when I started the actual movement, I did I listed the entire thing.
So how did you get there?
I tried to work it out.
Sorry?
I tried to work it out. I thought that's enough for the CNF. That's why I just did the next step.
Okay. Well, I will have to take a look at your actual answer, to see if there are any connections between the first part and the second part. Yep. Go
If
ahead.
you send y to that parenthesis that you have negative x, negative y, negative and c, y and negative y gives you 0.
See again?
When you expand that y to the
Okay,
negative x.
Okay. I cannot tell which part of the screen you're pointing at.
Okay. The part that you're trying to.
You mean down here?
Yes.
Okay.
The third one and the last one.
The third one
Yes, and the last one.
and the last one.
So when you expand the y inside that, it gives you y in this junction with negative y, right?
Okay, so the refutation step basically says this one and this one can be combined.
Okay.
Okay? So in general, the way refutation works is when you have A or B on one side, and then you have not A or C on the other side, then you can combine these two into a new term, okay? And the new term is not going to conflict with all of the other terms. And the new term is going to take what is remaining, which is B on this side and C on this side, but you will still be doing a OR. Is that okay?
Yeah, but my question is, you're looking to get a 0 in your answer to prove that the theorem applies with that y is wrong, right? So when you want to use negative y makes it correct, right?
No. The theorem is the negation of y.
The theorem is negation of y, but you're using y.
Which is the
that y
negation
is
of the
wrong.
theorem.
Okay.
Yeah, y is the negation of the theorem. Because you want to prove that if you put the negation of the theorem into the system, it will lead to a contradiction.
Okay.
Right.
So that contradiction shows up as a 0, right?
Yep, it's the third step. So
Third
we're
step.
not there yet.
No. What I mean is like, why you didn't just use y and negated y?
Y and negated y, but there's no negated y here.
The
There's
third
no
step
negated
is-
y all on its own.
No, I mean like, if you expand that y in the 3 terms you have on the left. So y in conjunction with negated x, y in conjunction with negated y in conjunction with c. When you have this junction between, right?
Okay, let me see if he can clarify. Go ahead.
I have a completely different question.
Oh, okay. I was thinking, I was hoping that you were
Maybe
you were trying to clarify
Can you
again.
combine the first term and the third term to get negated y? Or can you not combine triple?
In one single swoop, probably not a good idea. You can do it in 2 steps, okay? Because in each step we only take out one term. Yep. Is that what you were saying or not?
No,
I don't
I'll
think
talk
that's
about it later.
okay. So there are several ways to do it. I mean, one way to do it is what he said. You know, you can take this term here and combine it with this term here, but you should only take out one term at a time. That's basically one step of resolution by refutation. So when we combine it in a different way, so when we work out the way that I chose to do it, I would combine these 2 terms. That will take out the y in this particular term, and this thing just reduces to false, okay? But if you use a or false on anything, it is just not doing anything to it, and that's why we only have this portion left. But everything else is still the same. So these ... is representing what we have up to this point. But on top of all of that stuff, we can also say, hey, we also know that not x or c has to be true, okay, which is okay. So now what we do is we take this term and we say, hey, how about we combine this with x all by itself? That will take out the negation of x, and we only have c left. When we have c left, we'll take this term and combine it with not c, and that will basically give me a term of false. But whenever you have a term of false, which I use a 0 here to represent, is a contradiction. So when you get to a contradiction, you can stop. You can basically say, if I introduce the negation of the theorem into the system, I can get to a contradiction. Yes, go ahead.
Do we not have to prove that the known facts don't cause a contradiction?
Say again?
Do we not have to prove that the known facts don't cause a contradiction? That was step 2 in the example 2 in class.
Right. In the homework question, I did ask you to make sure that the given facts do not lead to a contradiction, but it is not asked here. If you did that, I'm not going to take any points off. Did you get to this part too? Did you
Yeah.
prove that the theorem itself is true?
I actually didn't do that. I was just asking for.
Say again?
I didn't do that. I was asking for.
Oh, okay.
So if you did do that, because I checked that and they did come to a contradiction for me, so if I stopped there, is that okay?
You mean all the given facts lead to a
Yeah,
contradiction?
Yeah.
Okay, so you mean this part here is already leading to a contradiction?
Yeah, mine was a little different. What did I do?
You might, that should not get to a
Because my
contradiction.
CNFs were a little bit different, so I don't know if I'm fully correct, because I distributed the or, like the very last term, instead of the giant, like the third term. I distributed the or across.
Oh, you mean
So
here?
yeah, right there. So I had C and not X, or C or not X, or C or not Y. I don't know if that counts as a CNF though. Is it like one giant one still?
But you cannot distribute a.
Because I found the rule for that in our
Okay.
axioms.
But distribution only works when you have a different operator inside.
The one I was looking at is distributing or over or.
Okay. But that will still only give you a gigantic or
Yeah.
over here.
Well, what it gave me was C or not X or C or not Y.
C or not X or C or not Y.
Yeah.
Which is okay, that's not a problem.
Okay, so then when I was checking the facts, I combined C or not X with just X, and that gave me just C, and then I have C and not C. So then you have a false.
Okay, so let's take a look at this. Okay, so what you ended up with, okay, I'm gonna use the notepad here. Okay, I can understand how you can come up with the term. So you basically end up with not X or C as one thing, and then the other one is not Y or C.
Yeah.
Okay, which is okay because with disjunction, because of the associative law, you can dissolve the parentheses. It becomes just one big disjunction with 4 terms. Okay, so in other words, what I want to do is to establish what you have. It has the same meaning as what I have on the board. Okay, so when you look at this whole thing and you take away all the parentheses, it just becomes one big or. And because we have commutative law also applicable to disjunction, you can move the terms around as many times as you want. It doesn't change the meanings. So when you move the terms around, you can end up with putting this or C all the way to the end here. And when you have C or C, it is the same thing as C. In other words, it's not any different from the one that I have. So the fact that you can get to a contradiction because of the given facts is probably because of the resolution part. And I'm not quite sure whether it can lead to, it should not be able to lead to a contradiction. In other words, if we just look at this part here, that should not lead to a contradiction.
Because what I have is one of the terms is C or not X.
C or not X.
And then I put that with X, and that'll give you C. And then
Oh, I see what you mean. But it is actually a part of a bigger disjunction.
Okay.
You cannot just take that part out.
Okay.
So if you take this part and and merge it up with this part here, you would still have the other part left, which is not C, not Y or C, and that will cancel out with this one here, but you end up with just true left, which is not a contradiction. And that's why when we do resolution, we can only apply one variable at a time. Okay. Are there any other questions? Yep.
So how about if I got this in like 5 or 6 steps instead of 3? Is that okay?
You can apply more steps, but that's fine. Yeah. It's just that you have to apply the steps correctly. The main point is every time you do a resolution, you can only cancel out one variable at a time. When you cancel out 2 variables at the same time, it doesn't work out. It doesn't work out. I can show you why it doesn't work out when you cancel out 2 variables at the same time. Okay. So I'll give you this one here. I think we have seen this one before, but we'll go ahead and take a look here. Okay, so let's say we want to say A is equivalent to B. That's all we're going to say. Okay, which by itself cannot be a contradiction. Is that okay? Because if I only give you the fact as, if A is true, B is also true. If A is false, B is going to be false. If B is true, A has to be true. Excuse me, if B is true, A has to be true. If B is false, if B is false, A has to be false. If I give you those facts, it should not lead to any contradiction because it's open-ended. So let's take a look at how we can convert this into CNF. So to convert this into CNF, we can basically break it up into A implies B and B implies A. That's basically the definition of is equivalent to. Are we still doing okay so far with this? So the next step is to take out the implies and substitute the implies with the negation of the first part and then an or for the operator. So now it becomes not A or B and not B or A. Are we still doing okay so far with this one? Now if you apply resolution on both terms at the same time, then you end up with, hey, we have a contradiction. But it doesn't work out that way, okay? You have to do it with one variable at a time. So with one variable at a time, you can combine either, you can get rid of the A first, or you can get rid of the B first. So I'll just pick A and see what happens, okay? So we'll still have not A or B, and not B or A. And now, since this time I'm only getting rid of the A term, I would have B or not B left. Are we doing okay so far? I'm combining the first two terms and then use A as a resolution, kind of like quote-unquote pivot point. And I end up with B or not B. B or not B is not contradiction. In fact, it is quite the opposite of a contradiction. It is just true itself. In other words, this whole thing, if I look at this, B or not B, it is just one, or true. And anything anything and true is just anything itself. In other words, yeah, I can apply resolution, but it doesn't go really quote-unquote anywhere, or at least it doesn't help me to get to the contradiction that I'm looking for. Is that okay? All right. Okay. All right. So if this one is okay, we're going to move on to question number 3. Are there any other questions about number 2? Questions on number 2? All righty. We'll move on to question number 3. Okay, question number 3, and if you look at the rubric, okay, this one I kind of like too, because it is also, I think this is just about the right difficulty level. Not too much, not too little. It's just about right. Okay. So we'll take a look at what the question is asking. The question is asking, in general, can we say that the summation of I going from 1 to n is, ni, is n times n plus 1, and then the whole thing divided by 2. Okay, that's the theorem, okay? I'm not really sure whether the theorem is true or not. I want you to prove it one way or another. Well, in this case, I want you to prove that it is true, okay? It is known that it is true, but I want you to prove it. And I want you to prove it by induction, okay? That's part of the question. There are probably ways to prove this one without using induction, but since the question explicitly asked that you prove it by induction, you have to do it by induction. And it suggests already in the question, clearly identify the base case and the induction step, okay? So if you identify the base case and the induction step without proving either one, you will get partial credit because, as a part of the question, you have to identify these two. And prove each separately, so the proof is worth extra points, in addition to being able to identify what is the base case and what is the induction step. The base case is when n equals to 1. Now when n equals to 1, the first term is just the summation of I going from 1 to 1. And each subterm is just I, which is 1 all by itself. But 1 is 1 times 2 divided by 2. This part is because of the theorem as well. And as a result, we have just proven the base case itself. The base case of proof by induction typically is fairly easy to deal with. You just have to pick a concrete number and say, hey, the theorem does work in this specific case. And typically you pick one end or the other end and just say, most people start with the small end, the lower end. And in this case, n equals to 1 is definitely the lower end. So that's a fairly easy one to get. You get partial credit by identifying what is the base case and proving the base case. The induction step is the trickier one. The induction step, basically you have to make an assumption and say the theorem is true for up to case k. So basically, without any proof, without any proof whatsoever, you make an assumption and you say, well, let's assume the summation of I going from 1 to ki is actually k times k plus 1, the whole thing divided by 2. Okay, so you can use it and say, okay, let's assume that's a fact. Can we use this fact to prove that it is also true for case k plus 1? That is the induction step. So by identifying this part here, just by stating this portion, you get partial credit. Without proving it, you already get partial credit just by stating, assuming it is true for k, we want to prove it is true for k plus 1. Now, I know some of you do not like k plus 1, so instead you say, assuming it's true for k minus 1, prove it is true for k. Just as good, not a problem. Go ahead. What's that your question? I can see it because I actually scanned through the questions, your answers, so I know some people use a variant of what I just said. It's okay. It's perfectly equivalent. Okay. So the proof goes like this. Okay, you start off with the beginning point of what we want to prove, and then the next thing is to break it up into this equation here, or into this formula here. Are there any questions about how I got this part done? I just took the last term out of the summation, pull it out of the summation, so it becomes independent to the summation. But in order to do that, I have to take that term out of the summation. So the summation is now going to one term fewer than before. Okay? But then I recognize, hey, the summation term is now something that I can actually recognize, and because of the assumption that the theorem is true for case k, I can now say, hey, this summation has a closed form of k times k plus 1 divided by 2. So I can now establish that part. Okay? So I did not actually do anything, I did not prove anything, I did not even derive anything. I just say, because of the assumption, we can now make this derivation. The actual math of this particular proof starts here. Okay? Going from this line here to the third line, I cannot highlight these things correctly. I think it has to do with how the math ML is actually formatting the whole thing. But if you look at this line versus the third line here, that's really just the math. I take k plus 1 and say, hey, I want to combine the first term with the second term, so I need to have the common denominator. So easy thing, 2 times 2. 2 over 2 is 1, so I just multiply k plus 1 by 2, and then I add it to the other one, and then I apply from here, from this particular term, I get to this term here. So which rule did I use in algebra? Starts with a D. Distributive law, right? It's the opposite of, well, most of the time when you apply the distributive law, you're breaking up something. This time I'm combining something. Because k plus 1 is a common term between 2 times the whole thing k plus 1 and k times the whole thing k plus 1. So I just look at k plus 1 as a common term, and then I say, hey, we can just combine the multipliers together, which is 2 on one side and k on the other side. So once I combine the multipliers into its own term, we have 2 plus k here. It still doesn't look like what we are looking for, so what I did was combining a few steps into one single one. The first one was I reversed the order, so k plus 1 is on the left-hand side. That's by the commutative law of multiplication. And then the second thing I did was to reverse the k plus 2, or 2 plus k, turn it into k plus 2. That's also the commutative law, but that's for the addition. And then I break the 2 into 1 plus 1, and then I apply the associative law to rearrange parentheses a little bit. Now, why do I rearrange the parentheses? Because I want this to be the same as this one here with the plus 1 on the outside. Now, if you did not actually go through all these steps here and you just end up with k plus 1 times k plus 2 divided by 2, that's okay. Okay, this is just what I like to do, because it fits the format of the theorem, and I want it to fit the format of the theorem. Okay. But if you get to k plus 1 times k plus 2, or even 2 plus k, okay, it's good enough.
Yeah, just left it k plus 1 times k plus 2.
Yeah, that'll be fine. But I just like this extra step to make it look like exactly the same format. Okay. Are there any questions about number 3, the proof by induction question? No questions? Okay. How many people have seen the proof of this particular theorem but not inductively?
I've seen it inductively.
Yeah.
Oh, okay. The inductive way is actually the quote-unquote easier way, but you can prove it without using induction too. Yep.
You can write it in like 1 plus 2 plus n, one right opposite y and n column.
Right, you can say the first term plus the last term is this, the second term plus the second last term, but then it's not, as rigorous, it's not as, mathematical. Yep. All right, moving on to question number 4. So, question number 4. And let me get to the comment here. Okay. Oh, this one I also like. I like every single question that I asked. Okay, this is finding maximum. It does not come out the way I want it. So I'm just going to write it out, using the editor here. So I'm going to just write it out here, but instead of just writing it, which is not going to be a whole lot of fun because most of you probably can just reformat the program, how would you approach this problem? Okay, the question text specifically said, I want find max to be recursive, and on top of that, I wanted to break into 2 problems, and each subproblem is about 1/2 of the size of the main problem. Okay, that's actually in the text of the question itself. So how would you go about doing it?
Base case.
Okay, you think about base case first. Okay, but what is a base case? When do you stop the recursion? Well, when the array only has one element. When the array has no element, you cannot say what the maximum is. So you don't want to stop when n equals to 0. But you want to stop when n equals to 1, because when n equals to 1, then you can say for sure, hey, since the entire array only has one element, that has got to be the maximum. Is that making any sense? Okay. So what if n does not equal to 1? What if it is 2? Well, 2 is the easy one, right? Because if you know how to handle cases of 1, when you have a case of 2, then you just say, hey, you figure out the maximum of this one single element. And you, on the other side, will handle the other element, okay? Now, of course, you don't know that with an array of only one element, it is really just the value of that element. So each subroutine call or invocation will come back and report, hey, this is the maximum that I found, and this is the maximum that I found. So now you have 2 maximums, right? One coming from one side, of the array. How do you combine those 2 maximums to be your answer to whoever called you in the first place? How do you combine 2 maximums coming from 2 different parts of an array to one single maximum? Is the maximum of those 2 maximums, right? Whatever is larger is the one that you report back. Is that making any sense? Okay. So that's the general idea of the algorithm. So when you have a general idea of what the algorithm is going to do, then you have to keep the same prototype. So we have const int star a, and then we have int n here. Did anyone forget the syntax of C and did not really quite know how to read the original algorithm? That's good. Then I don't have to send anyone back to CISP 360. Okay, so we'll handle the base case first. The base case is when n is 1, then it's easy to figure out the answer, because when you only have an array of one element, whatever the value of that element is the maximum. Okay, cool, we can do that. Right? Okay, so the else case is corresponding to when n is greater than 1. Okay, when n is greater than 1, it means it is at least 2, okay, which is good. So when it is 2, then we will use m1 and m2 to keep track of the maximum of each quote-unquote half of the array that I'm responsible for. So we'll say m1 will be the maximum of the first half of the array. The first half of the array, or the maximum of the first half of the array, can be found by just calling find max again. It has the same beginning as me, except the number of elements that needs to be dealt with is 1/2 of what I have to deal with. Is that okay so far? Okay. And M2, which is responsible to deal with the other half of the array, this is the only one part that is a little bit tricky because you have to say, oh, don't start with the same point where I'm starting off with. You start off at the midpoint of my starting point. Is that okay? Is that the right index? How many people do absolutely hate pointer arithmetics? Okay, fine. We'll do it without using pointer arithmetics then. That means the same thing. Don't you like C? Because C allows you to do exactly the same thing with 20 different gazillions. Yep. You do not need to move on one more because n divided by 2 is the exact number of elements the first call is handling, which means it serves exactly right as the index of the element to start with in the second call. Because we start with element 0, so okay, let's just say that n divided by 2 is 3. Okay, so this means that the first call will handle 0, 1, 2, 3. Right? But the second call is going to start with array. No, I take it back. Because n divided by 2 is the number of elements. So that means the first call will only handle 0, 1, and 2 as indexes because n is 3. So the second call will handle 3 and up, which is what it needs to. If you do any plus 1, minus 1 thing, it's not going to be a big problem unless it leads to infinite recursion. Because if you do a plus 1, when you specify n, you can potentially end up with an infinite recursion. Okay. What about the number of elements I have to deal with in the second call? It's not necessarily n divided by 2, because what if n is not an even number? But you know what? I get another trick too. That has to specify the remaining number of elements, right? Hold on a second here. Have we talked about something like this in this class? No. You guys do not remember? Okay, we did talk about something like this, not in the context of finding the maximum. Instead, what was the example that I used to illustrate how to find? Well, okay, I just spoke of the answer itself. Okay, what example did I use to illustrate how to break a problem into 2 equal or approximately equal halves?
Linear search.
Linear search. Yep, exactly. Okay, so you just look at the linear search algorithm and how I divide it into 2 equal halves. You go like, hey, that's about the same format as what this guy needs to do, because this one is not scanning for a particular answer, it's just looking for the maximum number instead of a particular key, but the general approach is the same. Okay, now that we have M1 and M2, I know what I need to return is one of those two. So what I'll do is I'm going to say, well, this is the way I do it. You don't have to do it the same way. I just say if M1 is greater than M2, then go ahead and return M1 because it's the larger of the two. Otherwise, return M2. I just use a ternary operator. Some people like to use a conditional statement, which is fine, not a problem. Okay, so that's the answer. The way this is going to be graded is going to be a little bit more work for me because I'll be looking for specific things about the recursion, like does it end, does it stop at the right point, okay? If it is, how about the recursive part? Does it divide the problem into 2 approximately equal halves? If it does, does it combine the result of the recursive calls and give one particular answer back to its own caller? So those are the things that I'm looking for, when I grade this particular question. The syntax, can be off a little bit. This is not a, C class, so if your syntax is not entirely correct, it's not going to be a big deal. But if the syntax is off enough that it changes the meaning of the program, then it becomes a big deal. Okay. Are there any questions about this particular one?
In our answer, would we be allowed to add additional parameters to our function?
You did not change the beginning of the array, right?
No, I.
You specify the range of the indexes?
Yeah.
I suppose it would still be okay because you can, okay, the reason why I said that is because you can have a quote unquote cover function that is non-recursive, but that is going to the starting point of the recursive function. So I can see how that might work. And basically you still understand the concept of breaking it up into two halves and do it recursively. So, in this class I would just say it's kind of okay. All right. Any other questions about find max? Did anyone do this recursively but without breaking it up into two equal halves? For some reason, I thought there would be.
I didn't really understand what that meant, really. I mean, I think I kind of
I misunderstood what it meant as well.
Huh?
I misunderstood what it meant as well.
Oh. Okay, I'm just reading my own words here because some people say that I have a knack of asking questions in a very confusing way.
Well,
if there's a more confusing way, I will find it and use it without even knowing it. And that's my talent. Not even knowing that I'm using the more confusing way to ask the question.
You always ask questions in a perspective that I never thought about before, so then I have trouble kind of quite grasping it. Sometimes, a lot of times I have to reread it maybe at least like 2-3 times, just like, because like a lot of times I'm just not used to asking questions from that perspective.
I'm sure that statement goes both ways.
Yeah.
Except in my case, there are 50 other ways that I did not think about. Because each one of you has a different way of looking at the question. Okay, re-implement find max recursively such that the original problem is broken into two approximately equal size subproblems. I'll take a look at the answers and find out what to do with it. Okay, question number 5. Okay, this is our favorite topic, lotto. Now, this makes me, really wonder one thing is, lotto community colleges, because I think some of the lotto funding goes into community colleges. So the question is, how much? Okay, and we look for community colleges. And we get 13.6% of all the income of lottery. So since its inception in October 1985, the lottery has provided approximately $28 billion to students in California's public schools. Below are educational institutions that receive lottery funds along with fund distribution. Well, even UC get 2.2%. Not sure how much that's going to help, but they get some minute portion of the lottery money. But it's mostly going into kindergarten and 12th grade schools, which is kind of, in a way, this is somewhat interesting because if the education system works the way it's supposed to, then nobody's going to play lotto. It's a good system to have. This is in engineering, we call this a negative feedback system, where the feedback, if you use a portion of the feedback into the control signal, it will eventually just kind of die off, and it's not going to go into oscillation state, or it won't just go uncontrolled.
So investing in that 80% really isn't working.
Apparently not. Maybe in the education they're telling people to play lotto. That will help feed the system. But it becomes an unstable system too. Positive feedback is not good. Not in engineering. In other ways, it's good. All right, this is the last question. Our lotto question, and this one is really intended to be easy and easy to get partial credit. So when you look at the way I'm going to grade it, you will probably agree that, hey, that's easy. Okay, step 1, if you read the question itself, it's broken up into step 1 to step 7. And I did it for a reason so that you guys can basically say, okay, I'm running out of time. I can only finish up to step 4. Okay, fine, you can get partial credit up to step 4. Okay, I'm not looking for one single final answer. If people say, I did not bring my calculator, well, that's okay. You don't need your calculator because I just need the formulae as answers. I don't need the exact numbers. Okay. Step 1 says derive a formula for the total number of unique tickets and call this x. Okay. So I did not even bother to define x here. I should have said x equals 2, choosing 5 out of 36. But in this case, it's a combination because order does not matter. Okay. So if I draw the balls in the order of 1, 2, 3, 4, 5, and 5, 4, 3, 2, 1, it's considered the same. So that's why we have to use a combination and not a permutation. Are we doing okay so far on step 1? Okay, and I picked Fantasy 5 because Fantasy 5 does not have a Powerball or anything that complicates the whole thing. It really is just the combination of 5 numbers. Okay. Step 2, derive a formula for the total number of unique tickets that match 4 out of 5 numbers and call this U. So out of the 5 lucky numbers, we'll pick 4 out of those 5. And then out of the not so lucky numbers, and we have 34 remaining of those numbers, just pick 1. And the product of those 2 become the answers. Are there any questions about step 1 or step 2? Step 3, basically the same thing, a rehash of step 2, except we're dealing with choosing getting 3 out of the 5 winning numbers. So if you only have 3 out of the 5 winning numbers, you also have 2 out of the 34 non-winning numbers. So you have to multiply those numbers together to get a total number of unique tickets. Any questions about these 2? Okay. Step 4. Okay, let's take a look at the really difficult step 4. Step 4 asks, derive a formula for the ratio. Okay, so that term ratio is telling you something. Hey, it's probably something over something. Of unique tickets winning 4 out of 5. Hey, I just saw a number that is 4 out of 5 before. Out of all unique tickets. So the only thing I can see that can go wrong is to reverse the numerator and the denominator. But because of the way the question is asked, it's already kind of telling you which one is the numerator and which one is the denominator. So even without steps 1, 2, or 3, I can jump to step 4 and get that partial credit. Is that making any sense? Yep.
So I have the same thing U over X, but I have 110 over the number of tickets equal U over X.
But that's not what step 4 is asking. Step 4 is just looking for the correct, the theoretical ratio, but not the actual ratio.
Isn't it should be the same? This one should be equal to this one.
What did you have again?
110 over the ratio. 110 over some number of tickets.
So did you mention anything like U over X?
Yeah, so this one which is equal to U over X, which is the
Okay, so you are basically answering a further question.
Yeah, I answered
in the earlier part.
Yeah, the fourth and then I got 6 together. But I did 6 again.
Oh, okay, you did 6 again. Okay, that might be okay.
I did this.
If you combine those 2 into one step, then I have to kind of pick out which one is which one. Go ahead.
What if I actually did like this and I solved it for R, and so basically I did step 4, 5, and step 6, 4, 4. But I redid it step 6 and step 7.
Okay.
So like I basically solved step 4 or 5, so then I got.
I will have to take a look at how you do it and see if I can pick out these individual partial answers.
I already did the same thing as 6 and 7. So
Okay.
they're all the same answers.
Okay. Well, but I am asking for certain things in step 1, 2, 3, 4, 5, 6, 7. So they need to be somewhere in your answer. Okay. Yep. So 4 and 5 about the same. Step 6 is asking, based on the exact number of sold tickets matching 4 out of 5 numbers, derive a formula for the estimated number of total tickets sold. So you're basically just preserving the same ratio, given that we sold 110 tickets that won 4 out of 5 numbers. This becomes the equation or the formula to calculate or estimate the actual total number of tickets sold. Yep.
I don't understand that part. Wouldn't you just get 1 since u over x is the ratio, which is going to be around 1 to 10?
No, because 110 is really the number of tickets actually sold. So let's say for a particular week, okay, a lot of people, my lecture videos on Lotto, went viral for 1 week, and the sales of Lotto tickets just plummeted to like 5 tickets, meaning 4 out of 5 numbers. So that can go in any direction, right? So the 110 can go in any direction. It's not indicative of the total number of tickets actually sold. Not quite sure whether I answer your question or not. The only thing we know is 110 divided by the total number of tickets actually sold should be approximately u over x. That much we know, okay? But we don't really know anything else. Did anyone actually go through the calculation and see whether those two numbers are about the same? Are they about the same?
They're within 100,000 of each other at least. 372,000 and 323,000.
So the order is right. The order of magnitude is about right.
Yeah.
Okay, that's all basically we're looking for. Because the number is really small to become to be accurate.
But
Yep.
how does that give us the total tickets sold?
I'm projecting the total number of tickets sold, and that's why we have 2 projections. Step 6 is one projection, and step 7 is a different projection. And those 2 projections should be about the same in terms of order of magnitude, but it won't be exactly the same.
So wouldn't u over x be equal to the ratio of 110 over the total number of tickets?
Yes. So in order to come up with a formula to come up with a total number of tickets sold, this would be the equation to do. Is that okay or not? U over x is kind of like a ratio. You can look up on the internet and you can actually say, you can determine the percentage of a particular grade of a particular class. Okay, so historically that information is out there. So once you know this is a class of 50 people, you can use that information and say, oh, okay, X many students are probably getting based out of this class because the ratio is preserved. So it's basically the same thing, but it's reversed. So instead of telling you how many people are in the class and asking how many people will approximately get A's, I'm telling you the opposite. I'm telling you how many people in this class are getting A's, and you have to infer or guesstimate the total number of students in the class. So that's the number 5. Are there any questions about questions 1, 2, 3, 4, or 5? No questions? Is anyone particularly easy so I can avoid it next year? Not this semester, next semester, so you can tell me. I'm just kidding you. Which one is more difficult? Which one do you think is the most time consuming? Number 1? Yeah. Number 1 has to do with how you think about the problem, how do you format the numbers. And kind of think it out a little bit, just actually writing out. We have students A, B, and C, and then with students A, B, and C, which one can share the same birthday with which other one, and what are the chances of that happening? Wait, we still have we still have about 7 minutes, 6 minutes now. 6 minutes. Yeah. So, we want to use the lot of money to the greatest efficiency, right? So we gotta make sure that we make use of every single minute. And plus, if I don't do that, I might get dinged for REC and RSI. Do you guys know what is REC and RSI? No. Who's taking an online class this semester right now? Okay. And do you guys know that the district office is sending auditors to online classes to audit basically a whole bunch of online classes for what we call REC and RSI. REC stands for regular effective contact, and RSI stands for regular substantive interaction. In other words, they are checking whether your online professors are initiating contact with you, reminding you, hey, are you guys studying for the test? Do you have any questions about the homework, and so on and so forth, instead of just letting D2L do all the automated grading and grade distribution, and the professor can sit back and do absolutely nothing. So that's what they're doing. Because I don't want those auditors in this class face-to-face and say, hey, Tech, you're letting students out 5 minutes early. So we'll just talk gibberish and whatnot until the time runs out. All right. So I did prepare a little bit more stuff for graph theory stuff. So let's go there and just take a quick look. Okay? Just because I spent time to work on it, you guys have to spend time to read it. So, okay. Go. Recursion, probability, graphs. There we go. Okay. So when we look at graphs, this is a link that I found that is really helpful. So you might want to take a look at it. In fact, you should take a look at it. The first half is, it's okay. It's just a whole lot of terms, so I'm not going to too concerned about the first part of this particular slide. But when you keep going, I hope it's not inducing any seizure. Okay, there we go. This is the good part. Okay, so the good part has to do with cryptography. Okay, this particular article did not explicitly state, how it is related to cryptography. So I did, some writing myself too. So what we'll do is we'll take a look at some traditional cryptography thing here. So Julius Caesar uses a very simple way to do encryption. So the way he does it is just by adding offset to the alphabet or the letters to make it easy, to make it not so easy to decrypt. You cannot just read the text and find out what it is. But there's one particular problem with this approach. Okay, if you look at a whole bunch of letters, okay, that are encrypted using this particular technique. In other words, you're just offsetting the letters by a fixed number of displacement or offset. What do you think would be one quick way to decipher the encrypted message? You don't know ahead of time how many, what is the offset. Okay, so I'm not telling you ahead of time that we have an offset of 3 in this case. Because to go from B to E, there's an offset of 3. 1, 2, 3. Okay, so the actual offset number is hidden away from you. So you're given a text that is already encrypted. So how would you go about cracking the encryption?
I might take a couple of snippets of word, or a couple of snippets from the text, and then try to compare them.
Okay.
I'll try doing it 3 this time. I'll try doing it 4 this time.
I like the approach of trying this and trying that. That's a general idea. Yep.
There are only 26 ways, so just
yep,
list all
exactly. There are only 26 offsets possible, right? Because you can only offset A to B, A to C, A to D, and so on, up to A to Z, which is only 25 actually, okay? Because mapping A to A is not considered encryption, right? Okay, and we have about 50 students in this class. So I'll just be assigning, like, okay, 2 people can work as a group and say, you are responsible for an offset of 1, you're responsible for an offset of 2, and so on. Out of the 25 groups of this class, 24 will be seeing something that is, hey, I have no idea, this is still gibberish to me. But one group will successfully do the decryption and say, hey, we know exactly what the original text is. Is that making any sense? Okay. So that makes this particular type of encryption not really useful. Okay, well, not by today's standard. So attack at dawn becomes, DWWDFN and so on. It's really weak encryption. So the next one uses mod or modular arithmetic. We already know mod, so I'm going to skip all the stuff about mod. So the next one goes like this. Okay, so this one is kind of interesting, a little bit more interesting. It basically has a keyword pattern. Instead of using a fixed offset, the position of the letter of the unencrypted text has to combine with a letter of a repeating pattern in order to come up with the encryption. In other words, so in this case, the actual keyword is math. In other words, we just repeat math, M-A-T-H, a whole bunch of times, okay? And then when the way you encrypt the original text is you pair up the text of the original text with one of the letters of the repeating M-A-T-H. And then we do a modulo arithmetic. In this case, there's a modulo arithmetic to wrap it back to the original text space, which is 26, and that's how it works. Okay? Now this one is harder to crack. In other words, if you did not know that math M-A-T-H or the length of the keyword is only 4, it gets a little bit harder to crack. Is that okay so far? Because the total number of ways to arrange the keyword, even if I told you the keyword is between 4 to 7 characters, that would still give you a lot of possible combinations. Okay? But there are still easy ways to crack this kind of encryption. The weakness of this kind of encryption is it is mapping a single letter to another letter. Now, why do you think that is a relatively weak encryption? In English, certain words, go ahead.
I was just going to say, because then it's just a matter of going through all the combinations.
You can go through some of the combinations, and you can try to identify the repeating pattern. In other words, certain things are almost certain to happen in any type of communication. So the word is, of, at, and so on and so forth. Those should happen fairly frequently. So we can probably get an educated guess of at least the encryption, at least a part of the encryption keyword, and then you can try to reapply that to the rest of the text and see if you can get something out of it. Yep. Yep.
Wouldn't like the like those vowels, wouldn't they be mentioned more than the regular letters? Like as encryption?
Again?
Like the vowels would be more like mentioned more than
it would, but since it's mapped to something else, we don't know, when you look at the encrypted text, we don't know whether it originally came from a vowel or not. Yeah.
Seems hard to decrypt, doesn't it?
It is harder to crack. It's harder to crack than the previous one.
Well, from there, it says T and A gives T, and also A and T gives T.
Right.
So how would you decrypt from T back to
okay, wait,
A
hold on a second here. Okay, this is the original text, right? This is a repeating pattern of the keyword. It's math, 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 okay? And this is the actual result. So what you need to do is you take this one here, you subtract this one from it, it becomes this one here. So the subtraction and the addition are basically modulo math. You're not just really adding or subtracting, but you're doing it with a mod 26 type of system. Yep.
So, if you're given the encrypted code, that would give you a possibility of literally billions of different combinations of possible keywords.
Given just the encrypted text, it would take it's much harder to come up with the keyword. Unless you know everything, all the communication starts with a certain pattern. That is the Achilles heel of the German encryption in World War II, because the German Air Force always start a communication with a certain phrase, okay? And knowing that is always started with a certain phrase, the Allies or the British already know, okay, so this sentence translates to this encrypted text. And from that, it is a whole lot easier to go backwards to figure out what is the actual encryption mechanism. Because they knew this is the plain text, it is now translated into this encryption text. That gives them a really big edge in terms of getting a head start of encrypting the text. So this one is the same thing. If you start with always a pattern, especially if it's a long sentence, that will cover at least the length of the keyword itself. It's just like that to crack the encryption. All right, so I know we're running out of time, so we'll continue this topic next time. And go ahead and read the text, and we'll talk about all this stuff on Thursday.